Hyunju was a professor at the University of Alaska Fairbanks. Hyunju did her PhD from University of New Hampshire and her postdoctoral training at the University of New Mexico, Albuquerque, and NASA Goddard Space Flight Center. She is one of the pioneers in the machine learning in the field of space physics. She was awarded $4 million by NSF to start the machine learning research in space physics in 2018. She established the Magician team, machine learning algorithm for geomagnetically induced current in Alaska and New Hampshire. She is our primary chair for ML-GEM resource group. Now let's give a big welcome to Hyunju Kano.
Yeah.
Baby there.
You can see barcodes everything.
Yeah, you guys already mastered my talk now. Okay. Yeah, thank you, Jaya, for introducing me. And it's also an honor to give these tutorials to this GEM community. And I will also tell you that this is my first time to giving a plenary talk. So it was very stressful to prepare the talk. And also I'm very nervous, so please be kind to me. Okay. Today I'm going to talk about the machine learning based geospace environment modeling and ML-GEM. And I would like to acknowledge my co-chairs, Matt, Shangning, and Bashi, and Gautam. And yes, so we're going to start this ML-GEM from this year. And I would like to advertise this session at the end of this talk. Before starting this talk, I have to acknowledge our wonderful magician team. So the magician stands for machine learning algorithms for geomagnetically induced currents in Alaska and New Hampshire. And we are a joint team of space scientists, computer scientists, and education outreach designers at various career stages. And we have over 20 members in the past, and it's continuously growing. And our main goal is to develop the machine learning algorithms for predicting space weather and also providing advanced warning of hazardous geomagnetically induced currents. And I would like to thank again all my early career scientists and graduate students in our magician team who helped me to understand these machine learning techniques. I learned from them. They teach me, and that's how I can stand here. And I especially thank Gautam and Doa and Matt, who helped me a lot to understand these machine learning techniques, and I need your support continuously. Okay, so this is the content of my talk. I will first introduce these basics of the machine learning, and then I will talk about the machine learning applications to the heliophysics research, and then I will talk about our machine learning ML-GEM resource group, and then I will ending my talk. Okay, let's just start with the machine learning basics. So machine learning is a branch of artificial intelligence. So you can see a large circle, there's artificial intelligence, and part of it, small circle, there's small middle circle is the machine learning. So machine learning is a part of the artificial intelligence. And machine learning allows computers to learn from data and make decisions or predictions without being explicitly programmed to do so. If you have a physics-based model, you have a set of each physics equation, and you have to solve that equation with your code. But machine learning is different. You set the input and output and let the machine to learn the relation between an input and output. You have no role to determine the relation. Machine determines for you. And then there is a smaller circle called the deep learning. A lot of people use this neural network, also called the neural network. So deep learning, neural network, it's a kind of same meaning here. Okay, so now we have to learn about the stages of the machine learnings. You first have to have a project. You have to identify the goal and choose the flexible solution. For magician team, we want to understand geomagnetically induced currents. However, the data is not widely available, and therefore we decided to predict DBDT patterns instead, because this DBDT pattern can trigger the hazardous GICs. So we found a flexible solution, and then we start the machine learning. To start the machine learning, you have to collect the data. Can you see my mice? Okay, good. Yeah, you first need to collect the data, and then you have to pre-process the data. Some data are redundantly used there, or some data qualities are poor, and some data are missing. So you have to fill those missing data gaps. So this procedure is the most important part of the machine learning. If you have a bad data, your machine learns the bad behaviors. So you have to make sure you have a good data set ready for the machine. And then once your data is ready and you look at your problem and look for all the other machine learning techniques and find the best model. And then you train the model, and then you evaluate the model. And oftentimes your first model isn't the best. So you have to do the tuning, fine tuning of your model. And we call that stage as hyperparameter tuning and optimization process. And once your model is mature,
大学習、
歌謡集。
今から。
今、しようってなんか、
it was great to hear your voice. I do not know who this person is, but thank you. Okay, and then once your machine is matured, and now your machine is ready to predict and also deploy to the community. And now that is not end of the machine learning. Your observatory will continuously bring you a new data set, and you have to wait until the enough amount of data are accumulated, and then you have to train again. So these are the never-ending procedure. The more data your machine sees, and your model performance gets better. And then now, there's a multiple machine learning techniques, but if you can divide into two categories, then there's a two techniques, supervised and unsupervised machine learning. In supervised machine learning, inputs and outputs are categorized by the modeler. And then machine learns the relation between the input and output. And here is a good example. You have a tomato images and you label them. This is tomato, tomato, tomato. And you have a multiple carrot images and you say it's a carrot, carrot, carrot. And then you also have a bell pepper. You say it's a bell pepper and bell pepper. And now machine learns that labeled data set behavior. And now once they are matured, you provide the images. And then model can tell this is carrot, bell pepper, and tomato. And this supervised machine learning technique has been widely used in heliophysics. For example, you have solar wind and IMM input, and then you want to know geomagnetic field disturbance. Then you determine the input and output and let the machine find out the relation between the two parameters. And then unsupervised machine learning, you basically let the model do everything. You throw a data into the model, and then model will look at the data, find the hidden features, and grouping them. And this technique has been used for aurora image classification. If you have a semi-aurora images, and your model can tell this is diffuse, discrete aurora, or there's a moon, clear sky, or etc. Yes. And now I would like to talk about the one part of the machine learning technique, the neural network or deep learning. A neural network basically mimics the human brain's behavior. You have an input and your brain processes the information and provide the output. Our machine do the similar thing. You have an input and output, and there's you have an artificial brain we call artificial neural network. And now let's look deeply into what's inside. if in the human, we have multiple neurons connected each other and processing the input data and then provide the output. If you look into the machine, our machine structure is very similar to our human brain neuron structures. And now let's talk about the neural network basics. Here is how the neural network look like. You have input layer and output layer, and anything in between, it's hidden layers. And then these blue dots are called neurons or nodes. And you can see there's a lot of connections. So what happened is that you have some input variables provided to this neuron, and neuron process the data and provide the output. That's how system works. And let's look deeply into this one neuron. And again, you have input values. I name it Y1, Y2, Y3. And then this neuron receive all the input variables. And then this link have a weight. Some input variables are more important than other variables. So you have a select the weights. I mean, your machine selects it for you. So your machine will select random weights here and then combine them. So you can see weighted sum of these input parameters and also have a bias input. And now your model create this weighted sum of input variables. And now this is not the output of your neuron. Actually, you have to use activation function that provides nonlinear feature of the neural network. So activation function calculates the output of the node based on its individual inputs and their weights. And there's a multiple different activation function that you can use, but here I'm going to show you two examples. One is sigmoid. So if G is not hitting certain threshold, it's 0. And if it hits certain threshold, it gives some values. And then that transition is kind of smooth. This is very nice, not like a step-like structure. And also another activation function is called the rectified linear unit and ReLU. And then this one, if your G doesn't hit certain threshold, they stay 0. And then if it hits certain threshold, it will give you continuous increase of the output as a function of G. Okay, so now you understand how each neuron works. You collect inputs and calculate the weighted sum, and then use your activation function and determine the output. Now let's go back to the bigger picture. Here, as I told you, here is input layer, output layer, hidden layers, and then each nodes have some connection. You see that this one doesn't have every connection because their weight is 0. So that's why it's not shown here. However, what I wanted to say is that each connection has a weight and each neuron has an offset. And also each neuron has a nonlinear activation function. And you can see, for example, this one, it utilizes these two input variables and give you an output value. And then this neuron also receives 3 different input variables and provide another output. And this output layer also received 5 different input variables and determine final outputs. And then now your question, how can we set the weights and offsets correctly? That's where your data is needed. You throw the data to the model, and model try all the random sets of weights and bias and find the best set that provides the best model outcome. And then how does model knows that their model performs better? That's where you need loss function. Loss function measures how good a neural network model is in performing a certain task. Here you will see the similar neural network, input layer, output layer, there's a hidden layer, and they predict some outputs here. And then now you have a target value, observation, real observation, and you compare these two. If their discrepancy is big, the model come back and train again to find the best outcome until this loss function becomes reduced. And there's a lot of loss function exist, but I can give you only 2 examples here. One is mean squared error, and another is mean absolute error. However, scientists got smart, and they introduced physics-informed neural network, PINN. They use physics equation as a loss function. For example, you want to predict geomagnetic field data. Then you know divergence B is 0. So you can provide divergence B should be 0. So once your output Bx, By, Bg is provided, and you calculate whether divergence B is 0. If not, you tell them this is wrong, machine, retrain it. That's what you can do. And then now, let's talk about the data split. You have tons of the data, but you have to split into 3 sets. One is training data set, another validation, the last is test set. And what you have to do, the training set is the majority of it, 80% of it, that's a recommended one, but you can always changing it. And then 10% validation. These two will be used during the training process. Your training data set will you give the training data set to the model, and the model try all the random set of weights and bias and provide the outputs. And then your validation data set used to calculate the loss function. Oh, your model prediction is wrong and loss is too high, and go back to retrain. And the model do this one iteratively, and then finally ended up with one single nice model and comes out. And then when you ended up with one nice machine learning model, and it's time to test your model performance with test data set. Because model already saw the validation data and the training data during their training. So you have to use a test data that model never seen to correctly process your model performance. Okay, now we have a one good, nice model ready. And then you evaluate the model, and it's normally not that great. And you have to look back, what can I do better? And that's the stage of hyperparameter tuning and optimization. And this stage allows data scientists to tweak the model performance for optimal results. And hyperparameters are the parameters that are explicitly defined by the user to control the learning process. Example, how many layers you want to use and how many neurons you want to use. And if you have so many neurons, then sometimes model get confused. You have to let them forget some information. That's where the dropout layer comes out. And there's a multiple way of fine-tuning your model, but this is basic, so I'm not going to introduce everything. Okay, now you learned all the neural network basics. As you learned input, output, hidden layer, weights and bias, and activation function, loss function, data splits for training and validation and testing. And also you learned hyperparameter tuning and optimization of your model. Now, let's go to back to the stage of machine learning. Yes, you collect the data, pre-process it, and then find the right model, train, evaluate, tune them, and then provide your model, perfect model or wonderful model to your community. However, how do I know I choose the right one? Here is some ML technique examples. Recurrent neural network processes time series data and finding the pattern in that time series data and predict what's coming next. That's what they are specialized for. Convolutional neural network recognize patterns in the image. I will tell you, this is a very powerful tools. If you're running the model, your input parameter easily go over 100 and 700, even 1,000. Then model having a difficulty to understand this huge data set, or your computer resources cannot process the data. You have to reduce your dimension of the input. Then you can create image with input variables and then let the convolutional neural network figure out those input patterns, and then using that pattern as input or output of your machine training. And then residual neural network is evolved convolutional neural network. We found that the convolutional neural network is having a trouble to have a deeper network. Deeper network means you have many hidden layers. So if you have many hidden layers, CNN cannot do well or they broke. So they found residual neural network techniques. And also I already introduced physics-informed neural network. You utilize your loss function based on the physics equation, and then you get better outcome. And I would like to also introduce explainable AI. This explainable AI helps the users to understand the model behavior. Why my model predict this? Because of what input? That's what explainable AI can give you the answer. Okay. Now I finished the first portion of the talk, and now let's go to the machine learning application of heliophysics research. And I would like to say that in GEM, we have 5 research areas: solar wind, magnetosphere interaction, and magnetosphere, ionosphere coupling, inner magnetosphere, magnetotail and plasma sheets, and also global system modeling. And I would like to start with MIC1 because that's my comfortable area. Okay, so for early career scientists or students, this is MI coupling basics. So when we couple the magnetosphere and ionosphere, we use current continuity equation. So when you have a field aligned currents coming from magnetosphere down to the ionosphere, we assume this current should be closed inside of the ionosphere. That will give you a current continuous equation, like as you see here. So what that means is if your horizontal current is diverging, that means your field aligned current should come down. And if your horizontal current is converging, then field aligned current should go up. That's what you show in this equation. And then if you are using the Ohm's law, horizontal currents can be a function of the conductance times electric field. And then if you consider electric field is electrostatic, then you can explain this electric field as a electrostatic potential. So this is a widely used approach for high latitude, for solving the high latitude ionospheric electrodynamics. Okay. Why I'm talking about this? Because I want to solve this equation with machine learning. So I was look through the literature and I found the Bharat-Kunduri's field aligned current model. He used convolutional neural network with 7 years of NASA Omni data and ampere field aligned current data. And their input is 60-minute history of solar wind, IMMF, and geomagnetic indices, and output is 2D field aligned current map. And here you are looking at the model results, and I would like to show this is IMMF BY and BG, and you can see this BG is turning from northward to the southward. And then left panel shows the actual ampere dataset, and right-hand side showing the convolutional neural network model results for 4 different time frame when IMMF turning from northward to the southward. And his paper said that the CNN model was well capturing this gradual response of field aligned currents to the time varying input conditions. And this is a new capability that traditional empirical model cannot provide. If you're thinking about traditional empirical model, they have using single time solar wind condition, IMMF condition, and give you the average condition of ionosphere. So you don't really, this kind of empirical model does not really consider this dynamic response of the system. So that is a big improvement from the previously available field aligned current model. So when I see this model, I got excited and I contacted Bharat directly. Bharat, can I use your model? And he said, it's already open source. Oh, go download it. So I was excited and downloaded it. Okay. So now my postdoc and Gautam developed machine learning based auroral ionosphere electrodynamics model. What this model do is to predict high latitude ionospheric electrodynamics in response to time-varying solar wind, IMF, and GI conditions by solving this current continuity equation with machine learning models. And already introduced Barak-Kunduri's field-aligned current model. But when we developed this model, we didn't have a machine learning conductance model, so we have to use empirical conductance model. Moen and Braque gives a solar irradiance caused conductance, and Robinson's new formula gives a conductance as a function of field-aligned current. So we use Barak-Kunduri's field-aligned current to calculate the Robinson conductance here. And then once you have two parameters, you can predict ionospheric electric potential. And then once you have ionospheric potential and all the other parameters, you can post-processing the data and calculating horizontal ionospheric currents, Joule heating, cross-polar cap potential, geomagnetic field variation, and even GIC warnings. And here is ML-AIM results. Here is the model input. We give 60-minute time history of solar wind, IMF, and geomagnetic indices, as well as F10.7. Here you will see this orange shaded line. This is our input feature. And then this dashed line is our target time to predict. And once you're plugging in this input, and it will first calculate field-aligned current pattern using Barak-Kunduri's model. It's very quick. And then now that field-aligned currents goes to the conductance equation and calculate Peterson and Hall currents. Now you solving ion potential for solver comes from OpenGGCM. Thank you, Jimmy, for sharing your code. And then we calculate the ionospheric potential, Peterson currents, Hall currents, and Joule heating patterns. And now, wow, great. But how good our model is. So we did some statistical performance testing. What we did, we used 3,200 DMSP polar cap crossing in 2017, and we calculate cross polar cap potential. And we also did the same thing. We calculated CPCP from ML-AIM, Weimer 2005, the widely used electric potential model, and SuperDAN, data assimilated model. And right-hand side, you are seeing the predicted CPCP versus observed CPCP. Blue is ML-AIM, and green is Weimer. Orange is the SuperDAN. And let's look at the correlation coefficients. I was shocked. None of them going above 0.5. And I realized this is statistical model. Yes, we have a limitation. And also, I was surprised Weimer, the most widely used ionospheric potential model, gives a 0.39 correlation coefficient. That's the reality, everyone. And then now I was looking at the ML-AIM performance. I found RMSE, MAA, correlation coefficient. All these values shows better than other empirical model. In addition to that, we use 60-minute time history, and we can create the gradual change of ionospheric electrodynamics, a capability that no empirical model can provide. Okay, this is published in 2024, Czech Space Weather Journal. So now you remember, when we solving the ML-AIM, we used empirical conductance formula, and I wanted to improve it. So I asked my wonderful postdoc, Gautam again, Gautam, would you train DMSP data and get the machine learning-based particle precipitation? And he said, yes, he's an amazing scientist. So he has used residual neural network with 17 years of NASA Omni data and DMSP SSJ data. The inputs are 6-hour time history of solar wind velocity, solar wind condition, IMF condition, geomagnetic indices, as well as F10.7 and location and time. And then outputs are differential energy flux of precipitating electrons into the 19 DMSP energy channel that ranges from 30 eV to 30 keV. And our resolution is 1 MLT, 1 degree MLAT, and 1 minute. We think we can do better than that, but this is preliminary results, so we are fine with this resolution. This is model results during southward IMMF tunnel. What you are looking at is 5 different energy channels. Left one shows channel 3, 12 keV. Middle, this one, 4 keV, 1.3 keV, 400 keV, 400 EV, and 150 EV. And during northward, weakly southward IMMF, and then strongly southward IMMF. So when I look at it, I was amazed. I think I never seen the global spectrum of aurora precipitation ever. This is my first time. And of course, actually, model is existing, and that's also amazing empirical model. But this, our model is machine learning based, actually is the empirical model. I mean, yeah, it's a good model, I would like to say. So now, what I found is that as IMMF BG turns strongly southward, I found aurora over expands at all energy channels. And also we found this color shows differential energy flux. And you see the differential energy flux got enhanced, which means aurora brightening. And we also found soft electron precipitations at 400 and 100 EV level. That's in the cusp region. This has already been observed and reported by many previous literature. And also I found that the polar cap region for 100 keV is much smaller than 4 keV polar cap region. Here, polar cap region means I put the poleward boundary of aurora precipitation and then the area inside of that poleward boundary. And I found that the 100 EV polar cap is smaller than 4 keV polar cap. And I was thinking a little more, that's understandable. High latitude region, you have open field line. They are connected to the magnetospheres, and those energies are lower. And if you go to the lower latitude, mostly they are closed field line. If you are in the closed field line, there are so many ways of cooking your electrons to the higher energy level. So that's why you have probably high energy and then also larger polar cap size. And I also asked Gautam, my wonderful person, again, Gautam, I want to see the energy spectrum. So this one shows energy spectrum at 65-degree magnetic latitude and 0 magnetic local time. So you are looking at differential energy flux versus the energy for northward, weakly southward, and strongly southward IMMF. And I found that, wow, okay. And thank you. Yes. So yeah. Yeah. Okay. So you can see as IMMF. Oh, thank you. Yeah, as you see that as IMMF turns southward, can you hear me? Yeah. Okay. Okay. As IMMF turns southward, and I found that the differential energy flux increased. And do you see this plateaued region? If you are looking at the newer 2009, they define this as broadband aurora precipitation. And I also found this little high energy flux in less than 100 eV. And I think this is the secondary electron created by the aurora precipitation. So our MLPPM shows aurora expansion, aurora brightening, soft electron precipitation in the cusp, broadband aurora precipitation, and production of secondary electron. I got excited, and I asked my wonderful Gautam to create the geomagnetic storm. And this is the movie. And you are looking at all 19 DMSP energy channel. Highest is here, and it goes lower to that direction, and then next line, etc. Is it moving? Oh, okay, now it's moving. Great. And then the bottom one showing the IMMF BY and BG in two different color. Blue is BG and the yellow is BY. And bottom one is CMH. So you can see the MLPPM predicts dynamic response of global aurora spectrums to the time-varying solar wind, IMMF, and geomagnetic indices. This is a capability that no empirical aurora model can provide. And we also find very interesting phenomena. It will appear soon around this location, and I want to stop if possible. I'm not sure you guys can see. So I want to show you there's some very thin aurora arc in the sub-aurora region, and their energy precipitation is about 30 big. So when I first saw this one, oh damn, machine did a terrible job at this energy level. But I talked to aurora expert, and they told me, Hyunju, this is stable aurora red arc. Ring current ion precipitates and create the secondary electrons, and electrons are very fast, and you can see all across the local time. And oftentimes you observe at the night side region. However, the mechanism should occur on every local time. And this star arc happens during geomagnetic storm. And this is a storm. So I got excited. Yes. And we are going to study more about this event. And I realize I have not many times. Okay, sorry. And now we have to go for the SWMI one. And then now I would like to introduce Connor Bryan's wonderful study, graduate student of Brian Walsh. And he calculated solar wind, he produced solar wind propagation model. And what he did, he used recurrent neural network with 7 years of wind and MMS data to predict solar wind and IMMF condition at MMS location with wind observation at L1. So you know that the L1 location is about 230 Earth ready away from Earth. But what we really need is solar wind IMM condition at Bauschack nodes. So we do not know how this information propagates. And that's what he studied with machine learning techniques. And then his research is telling that the prime predicts better MMS observations than the other MVA techniques. And MVA is widely used technique to propagate solar wind. For example, NASA Omni data. And then now I will go to the MPS one. And I have to advertise our SEMIS Aurora Image Classification model. This is led by Jeremiah Johnson and Doa. And what we do is we create a semi-supervised Aurora, semi-supervised learning approach. So what we did, we throw 7 million SEMIS all-sky Aurora images during 2007 to 2020. We asked the model to classify this aurora into 6 aurora types: arc, discrete, diffuse, clear sky, cloudy sky, and moon. And then here you are looking at some of the results. And when they predict the aurora types, they also give a probability. So what you are showing here is you are seeing the model think this is diffuse. However, as the strong arc appears and they think this is discrete. And of course, always there's other chance of being an arc or a diffuse. So what I wanted to say here is 100% diffuse aurora normally not happens in our simulation. However, you can utilize this information to do the data mining. What you are looking at here is 24 SEMIS aurora station for 14 years. And then you can see this, if you see the green line, a green color, that's a discrete aurora. And then if you see the yellow, that's a diffuse. And the red is arc aurora. When we create this chart, we make sure that their probability is high enough to tell this discrete, diffuse, and arc. So this is reliable data set. And this data set will be publicly available after we publish this paper, currently under review. And then you guys can do the statistical analysis with this aurora data set. And then now I have to go to the inner magnetosphere. And inner magnetosphere scientists, you guys are amazing. I learned a lot from you. And then I'm following your wonderful footsteps. And I would like to introduce Xingning Chu's wonderful study about chorus wave. And as you know, the machine learnings are having a difficulty to create the active time predictions because our data is mostly composed of quiet time data set. And then therefore, traditional chorus wave model cannot predict the chorus wave amplitude nicely, especially during active time. And then what Chu did is that he created a new loss function. If your observation and model results are very different, then you give a very high weight so that the machine got surprised. Oh, I did very wrong on this. And then I have to readjust the weights. That's what he did. And he was able to predict the large amplitude of strong chorus wave during active time. And I also have to introduce this graduate student Maz study. He's a Jacob Potrik's student. And what they did, they utilized explainable AIs, and this explainable AI can interpret the black box model results. So basically, which input parameter impacts the loss and enhancement of radiation belt electrons. And then they said that this strong enhancement of solar wind pressure contributed these dropouts. And this is great. Okay, and I would like to say ML model challenges and potential solutions. Okay, data are still sparse in both space and time domain. So we need more observations. And also like other statistical model, ML suffers from regression to mean. Your data mostly from quiet time, so you cannot predict the active time very well. But Xiangning shows imbalanced regression technique may be useful for doing this. And then there's a black box approach. Yes, everyone complain you don't know what relation between the input and output, but explainable AI seems telling us what determines why AI determines this output because of what input parameter. And then I would like to say the challenges are the ML proposer. We have ML proposers have a difficulties to propose NASA HSR or NSF GEM programs. I hope that we have, okay, we have NSF officer, great. Yes, the reason is addressing science questions often relies on the performance of a proposed model. So let's say we want it to be ambitious. So we provide ambitious science questions. And the major weakness is we don't know your model perform well or not. So there's a risk. That's a major weakness. And then we decide to be more reasonable with the science question. And then reviewers come back, your science questions are not attractive enough. See, this is happening. So maybe we need a new ML dedicated program to foster the ML activities in heliophysics. And NASA recently announced a new program named AI Application in Heliophysics. I was excited and opened up the solicitation and suddenly disappointed. 200K, nice. 1 year support only. And you have to write 15 pages. And hey, ML modelers are normally early career scientists. Their job is not guaranteed. They have to write for 3 years support. 1 year is unstable. Please give a longer year support. But I understand you don't have much money in the program wise. Then at least give us the reduced proposal length. 15 pages, too much to take. Okay. In ML resource group, I know I'm already run out of it, so I will do quickly. We support the GSM, Global Sensor Modeling. And you guys heard physics-based modeling framework, MAGE model, or SWMF. They have a multiple physics-based model of different systems, and they connect them together to understand system science response. I want to do the same thing. Our MLGM chairs wants to do the same thing. We want to create machine learning-based modeling framework for heliophysics research. And I made acronym, terrible acronym, MLMFHR, and I'm proud of it. We will change. Yes. So these are all the available, not all, some of the available machine learning model. We want to do this continuously. Our goal is to advance system of systems science in Sun-Earth interaction from a data-driven perspective by developing this machine learning-based geospace environment model by integrating all community machine learning efforts. And here's our 4 sessions, and I will skip this one. And we have AGU session, everyone. We have a regular science session. We got wonderful number, SM001. Wonderful. Don't forget, number 1 in the SM section is our section. Please submit your proposal. And we also propose THUR session. We are waiting for AGU's decision, but we would like to gather SHINE community, CEDA community, and GEM community together. We'll talk about this single unified ML modeling framework. And this is last slide, everyone. Thank you for being patient with me. I would like to say that, one little bit more, Chris. So machine learning impacts on heliophysics research. Machine learning can discover hidden phenomena in the sparse data set and provide physical insights. We also provide realistic input for physics-based model. Conor O'Brien's model can provide better solar propagation model, for example. And you can also couple with the first principle model and then providing insights into this unstable eruptive nature of geospace station systems. And please read these 2 papers. And we can also serve as a great validation tool for physics-based model results. ML model is statistical results, and therefore you can use our model to validate your model's general behavior. And then machine learning also act as excellent data mining tool and aiding in event selection. So event selection is breezy, and so you can continuously quickly work on the statistical study. And then finally, machine learning can enable nowcasting of space weather without the massive computation typically required in the physics-based model. And I admit, the training the machine is not easy, not trivial. However, once training is ended, then you can use these results very quickly, input and output within a second. So we can do the nowcasting. And thank you very much.
We have time for a couple questions.
Thank you, Hyunju, for the wonderful tutorial. I learned a lot. And on behalf of the ground-based magnetometer array community, I'm wondering what contribution we can make between machine learning and the ground measurements. Thank you.
More data is always useful. Yes, and so when we train the DBDT patterns for the model, it was very difficult to get the localized peaks because we just don't have much information. So always more data sets are always useful. That's the principle of the machine learning. Yes.
Thank you.
Thank you.
Thank you, Hyunju. Very interesting review. I have only one comment. You nicely described the most popular family of machine learning tools, artificial neural networks. They have become very popular beyond our field because of the machine learning revolution associated with big data. However, if we go beyond LEO, the main problem which we encounter is a little data. So the set, sorry, I didn't mean to bring attention to this business. It's not the only way. You know, there are works developed by UCLA people, Chipping and colleagues develop vector regression machines, etc. So I'd like to draw your attention to this aspect of our specific GEM community. Our major challenge is the little data. Thank you very much.
Thank
Very
you very
interesting. I
much.
very much appreciate your enthusiasm in pushing forward this business.
Thank you. Thank you. Bye.
Hi, Hyunju.
Oh,
Thank you for all the shout outs. So as anyone who's tried to assemble one of these machine learning models will tell you, most of the time that you spend actually developing these models is spent in data set cleaning, data set preparation, etc. In an ideal world, if you could snap your fingers and make sort of these logistical pipelines for data better, do you feel like we should be placing more requirements on, like, say, missions for putting their data sets in like AI, ML ready formats? Do you feel like that would be something that maybe there could be more funding for? Apologies for the rambly question, but
No, that's an
where do you
excellent
see
question.
addressing this sort of data problem in a not in a sparsity of data, but in a format of data?
Yes, that's a very good question as well. Yes, because machine learning modelers may not know that data set very well. So if mission people can provide a nice clean data set, that would be wonderful. And so in that matter, I'm really thank the DMSP team to provide such a wonderful data set, 17 years of data set. So we were able to directly use such a data set. And also, speaking of the program, there is a NASA ROSES program just for providing the machine learning data set. And one of our Aurora model that we showed is actually part of that activities as well. So there is a way, but again, that's also 1-year project and 15 pages as well. And it's really typical for early career scientists to jump in and hope that Charlene can think about these issues.
All right, that's the time we have for questions this morning, but thank you so much for covering such an intricate topic. And I believe your research is really having a standalone session this morning, right? Yeah. So learn about it this morning. All right, so why don't, yeah.